Hey, you know what? It's 10 o'clock. So I am going to get started. So welcome to this webinar that Dunham Bush and Airflow are hosting on some chiller basics and some of the Dunham Bush offering. So first of all, thanks for coming. And I wanted to, I read one blog every day, and it just coincidentally happened that this blog showed up. So a lot of my marketing ideas come from this guy named Seth Godin. And a lot of Seth, the theme of Seth is being sort of getting out there and willing to face this imposter syndrome, and take on things that, in other words, it's okay to feel a little bit incompetent. And what I'm hoping for today is, yeah, there's going to be some people in the audience who know more about chillers than I do. Ahmad hopefully knows more than most or all of them. But I just, make it somewhere safe where we can start asking questions. One of the things I find when I talk to quote unquote experts is that they don't always offer a great deal of context. And I like to add a lot more context, just to make sure we're all on the same page. So that was sort of a nice theme to pop into my inbox this morning. So, and if any of you are interested in marketing, Seth is the grandfather of it. And so in the non-imposter world, Ahmad is also our speaker today. So I'm going to be presenting a lot of the material and then at times turning the mic over to Ahmad for more of his expertise. So he's got a long history in different parts of the world working with chillers. So Carrier, Johnson Controls, Daikin, and now Dunham Bush. So Ahmad, thank you for joining us today. And thanks in advance for digging me out of the holes that I put myself into as we go along. Okay. So here's the quick agenda. I'm going to do just a little take on how I look at the world of HVAC and specifically chillers. We're going to be doing a pop quiz, and I want everybody's patience with this. The pop quiz is going to pop up on your screens. I would like everybody to take the quiz. Why do I want everybody to take the quiz? Just to make sure, we all know that I haven't met anybody that hasn't either had to take their time to answer this quiz or made a mistake. So it's not to be like, ooh, you don't know anything about chillers, hardly. It's more like, hey, we're in a spot where we all need some additional learning. Then we're going to talk for sure about chiller components, talk about which types, and then the second half, we're going to be talking about more or less the questions that I have and I wanted to answer myself. So I wanted to scratch my own itch and get answers to some of these things. And finally, and hopefully, as this couple hours goes along, be like, why would we want to consider Dunham Bush when there's a Johnson Controls out there, there's a Daikin out there, there's a Carrier out there, there's a Train out there. Do you need a fifth option? And maybe you don't, but maybe you do. And with, if you're following along my blog, there's some reasons to be paying extra attention to chillers. Number one, there's a lot of data centers being built, and the chiller you like may not be available. And number two, I wrote a little blog post on VRF and how it may be not everybody's best friend like it was 10 years ago. So we're going to dig into all that stuff. So this is just my take on chillers so far. And I'm going to poke a little bit of fun at Ahmad. So Ahmad and Airflow are sitting together, and this is their product overview. And not being a person with a lot of chiller context, I look at this thing and I'm just like, oh my God, I don't know any of this stuff. I don't know what the models are. I don't know what the types are. I'm not, it's very uncomfortable. I see just a lot of pieces of equipment that I'm not familiar with. And specifically, we're talking about the upper half of this slide, but that's their chiller lineup. And maybe you've been in this boat before where I don't even know what question to ask first. There's so much stuff. So Can you advance to like one? Thank you. I try one of my strong suits is trying to boil things down into the most common denominator. And if you've ever opened up, like, okay, maybe some of you sub 30s don't see catalogs anymore, but once upon a time, if you had a Cook catalog or a Greenheck catalog and you saw how many pages were in that darn thing, and you just go, oh my God, I'm never going to learn all this stuff. And after a while, you go, okay, in the upper right-hand corner of this picture is a centrifugal wheel. It doesn't really matter if it's driven by a belt or a direct drive motor. And it doesn't really matter. It does matter, but it doesn't matter so much in understanding how it works, whether it's in a box that's an inline fan, an upblast fan, a downblast fan, or whatever different kinds of configurations. The principles of that centrifugal wheel does, hey, I do a modest amount of airflow, I do it against a modest amount of static pressure. And so it makes it easier to understand what the product does if you have sort of the fundamentals behind it. So in applying that to chillers, I look at these and I go, are they really all that different? Or, I mean, they are confusing in their own rights. There's a lot of little pieces and parts. But if we are able to break these things down into more bite-sized pieces, maybe it's not so challenging. And again, that's the, I like the colors on this. Yeah, I'm using different manufacturers' pictures because this is just sort of a basics class. Water-cooled chillers. Oh, here's the JCI York branded air-cooled chillers. And same fundamentals, just small deviations. So, and with any luck, these pop quiz is going to work out the way I want. It's 8 questions. I'm going to give you all some time to answer. Then we're going to go through the answers and kind of, this is more of a baseline for all of us to see where we're at. If everybody gets this right, I'll be really surprised. But here we go, sir. So we have some variety of answers A, B, and C. Great. Let's move on to the next question. Okay, a little variety. A little bit tougher question. The symptom is, the issue is you have a dirty condenser coil. How would you know if you didn't go look at the dirty condenser coil? Pop quiz question number 4. Which of those is a scroll chiller? This one's a little tricky, but you got a 50-50 chance if you're guessing. All right, arrows pointing at evaporator or condenser. Most, not all, most air-cooled chiller evaporators. What is running through the tubes versus the shell? Shell's on the outside, tubes run inside. Refrigerant, water, or ammonia? Chiller manufacturers always make their what? And last one. In other words, if you, well, there was no clear-cut answer for all these. So we're just going to go through the answers quickly. I'm going to lean on Ahmad a little bit to jump in too. Let's go through the answers real quick. All right. Identify the condenser, A, B, or C. The condenser is B. So we need to remember that from this picture, it's a little tricky, right? But it always goes, the evaporator is boiling the gas. The compressor is C, and it works sort of like a centrifugal fan where the inlet goes in the center and the discharge goes out the side. So you can't see the connection between the compressor and the condenser, but it always goes, we're evaporating the gas or the refrigerant, it's in a gas form, and then we compress it in the compressor, and then we send it to the condenser to turn it from a gas back into a liquid. So it has to be in this configuration. So that may save you, a moment when you're in a mechanical room trying to figure out which end is up and which end is down, especially if the pipes aren't labeled. Okay, let's go to 2. Air-cooled chiller evaporators are usually dual pass because you want them on the same side because you may not have access to piping on both sides. Does this ever deviate, Ahmad?
This one?
Yeah, for an air-cooled chiller, it's always dual pass. It's always in and out on the same side, correct?
Yeah, it depends from, like, if you are using DX or flooded, it can be from same side, but from the side, the length,
Oh, I
or
see.
from the like circle, the diameter.
Right, because some of your air-cooled chillers have flooded heat exchangers, and we're going to talk about that a little bit later. Okay, next one, Shalekwa, thank you. Everybody needed to think about this one, right? So if you have a dirty condenser coil, what's not happening? What's not happening is there's not enough heat transfer, extraction of heat to change the gas into a liquid. So that means that the pressure in the condenser will be higher. That's coming off the compressor. So it means the higher head pressure, the higher discharge pressure. If you had high suction pressure, it would be something to do with the evaporator. And of course, chillers will try to maintain the same chilled water temperature even when it's not performing well. So at some point, I suppose the chilled water will get warmer, but initially you'll get high head pressure would be the indication. Okay. And then you might not, well, the compressors on the right are scroll compressors. And it just, if you wouldn't necessarily know that, but they look sort of like packaged off the shelf scroll compressors, whereas the ones on the left look a little bit different. And that's because Dunham makes a vertical screw compressor. So it's B. This one, most everybody could have figured out if they had a little bit more time. So it's an air-cooled condensing unit, and the air-cooled is part of the condenser. So therefore, just by elimination, the bottom is the evaporator. Very good. And as Ahmad pointed out, this is maybe an unfair question, but typically, and this would be Carrier, Trane, JCI, they're air-cooled scroll chillers, which is the most common, has the refrigerant running through the tubes and the water in the shell. It's a great picture. Something that I learned that I didn't know when I started this is that, I mean, theoretically, we could go to the market and buy condensers, evaporators, compressors, controls, expansion valves, and build our own chillers. And more, the chiller companies are buying components and assembling. Not all, and not everybody makes this or that. Like, for example, that vertical screw chiller, Dunham makes it, but they buy other compressors, for example. And then like Danfoss makes a lot of, Emerson makes a lot of, and then there's a whole market for shell and tube heat exchangers too. So none of the above. And finally, and we're going to cover this more, the expansion valve sits between the evaporator and the condenser. Okay. So we're going to, yeah, so if you got, and you probably didn't keep track, but if you got 0 through 7 correct, then you're in the right place. And if you got all 8, well, good for you. I didn't get all 8 right of my own questions. So good for you. All right, let's press on, shall we? And we're going to put the parts of a chiller together here. So once upon a time, I did heat pump, just air-cooled heat pumps as part of a presentation. Boy, it sure is the same thing, less the reversing valve. So it looks different when it's in the chiller configuration, but this is all there is to it. Condenser, evaporator, expansion valve, compressor. And then there's some other parts that go on top of that, but that's the primary function. So let's go to the next slide. And Ahmad, maybe you can talk a little bit more about evaporators here. You said DX evaporators for scrolls. You know, what is the sort of the basic understanding that engineers and contractors need about evaporators? It's this, but.
Now, it is same functioning you will get same output from DX evaporator, from flooded evaporator. There is no change between both of them in terms of operation-wise, but how they work, how they are designed, this is the only difference. Now, when we speak about evaporator, everybody will come to know you have two types, mainly two types. There is a third type, they call it fouling films, but this is later on. DX means your refrigerant will go through your tubes. So you will get a smaller amount of refrigerant inside that shell because refrigerant, it's already inside your tubes or pipes and water is surrounding it. In a flooded is the opposite term. The refrigerant is flooding your water, which is inside your tubes in that case. Now, both of them, you can have pros and cons, but again, for you as a chiller, you look for output of the chiller as a system. It's not looking for each item inside, like, what about your condenser? What about your evaporator? What about, no, you are not buying items. You are buying one full system.
Yeah.
So the main difference, DX, you have less amount of refrigerant inside your system. Flooded, you have larger amount of refrigerant inside your system.
Okay. And then going to the next slide, condenser. Oh, there's just you'll have to click a couple times to liquid to get the last couple images. These are just more pictures of evaporators. Water-cooled condenser looks exactly the same as a evaporator. And then just the air-cooled condenser, we're taking that to remove, to remove the heat and condense the refrigerant. We're just using air instead of condenser water from a cooling tower or something like that. So that's what it looks like. Like we talked about, generally 2 pass for air-cooled chillers. And then when you get into the multiple passes, that's more for water-cooled systems where you're trying to fit more dimensionally. So you can shrink the footprint of a chiller by going to more passes, change the efficiency by going to fewer passes. Anything you want to add there, Ahmad?
No, nothing. Normally, what you care about when you design your chiller is your pressure drop to take note for your pumps. So if single pass is good, 2 pass is good, 3 pass this, based on your pressure drop mainly. But again, you look for your total efficiency of your chiller. You don't care about that item itself.
Got it. Okay. Then we're going to play a little video about chiller expansion valves because I think it does a nice job of articulating the differences between thermal and electronic, and we're going to just play that real quick. And Shalakwa, make sure you're sharing the sound.
Expansion valve we're going to look at is the thermal expansion valve. In the real world, the thermal expansion valve looks something just like this. So this one is actually on an air-cooled chiller, but it's still got the flow of refrigerant coming through and then going off into the evaporator.
Can you go to full screen,
the equalizer valve coming through there. And attached to the top of the thermal valve is the capillary tube, which goes off and measures the superheat. Now, these type of valves are usually found on smaller chillers. As they start to get larger, that's when they move over to the pilot operated valve to give much better control. So the thermal expansion valve is very similar to the pilot operated one, except that it hasn't got the main expansion valve there. The thermal expansion valve is the main valve in this type. So again, we've got the capillary tube rising up and connecting onto the suction line to measure the superheat. And we've got the refrigerant in the condenser, which will flow through, is being held back currently by the valve head. And once released, that will flow then off into the evaporator. So the pressure is starting to build in the capillary tube due to the superheat transferring its thermal energy over into the thermal bulb and expanding that refrigerant. That pressure increasing and pushing down the diaphragm, which pushes down on the pins and starts to knock the valve body off of its position, allowing some refrigerant to start flowing from the condenser and into the main valve. That refrigerant then starts to flow and goes off into the evaporator. And finally, once the maximum amount allowable superheat is there. The valve body opens fully, allowing the maximum amount of refrigerant to flow from the condenser through into the evaporator. So this type of expansion valve is exactly how you would find in a kind of, a household air conditioning unit, but the valve is just a slightly bigger version, obviously to handle the load of the cooling load, which it needs to for the size of the chiller. The third expansion valve we're going to look at in this video is the electronic expansion valve. Now, in the real world, the electronic expansion valve will look like this. You can see it highlighted in the circle here. Now, this type of expansion valve gives the best performance. And that's because the valve here actually uses a step motor in the body, and that precisely controls the positioning of the valve.
Well,
Yeah,
I think the long and the short of it is that electronic expansion valve has a much more accurate control in that you're measuring the temperature and pressure of the refrigerant and controlling the pin to release a more precise amount of refrigerant from the condenser into the evaporator. I actually have a question for you, Ahmad. When I always thought that the liquid flashed right after the expansion valve, or is there some collection of liquid at the bottom of the evaporator?
based on chiller design, yes, sometimes you'll have, correct.
You'll have some liquid refrigerant in the bottom of the evaporator?
Liquid receiver, yep.
Okay. All right, Chaleko, we can move on to the next.
But the side.
Oh, there it goes. That's okay. I think we've covered it.
Yeah.
Okay, thank you. Okay, now another element of chillers is the controller. And I wanted Ahmad to talk a little bit about the controller that they choose to use and the way they go to market. So this is a non-proprietary controller, correct, Ahmad?
Yeah.
If you could expand a little bit on that.
Yeah, now normally when you deal with your manufacturers, different type of manufacturers, different brands, this is the brain of the body, right? This what it controls your machine, regardless. It's a package, rooftops, HU, chiller, maybe small fan coil unit. Now, for us as a Dunham Bush, we deal with a company called Micro Control Systems, MCS. They are well known, I think, all over America. It's not only in Florida. They are based in Florida. But we do open protocol, non-proprietary controller, where the end user will not need to refer to manufacturer for a passcode or to call technician to come to give him an access or to do any like diagnostic or rectifying inside the control. Now, this company also, if you go to their website, you will find I don't know what they call it, but something compatible with existing like Carrier, Train, Daikin, Johnson Controls, any other brands controller. So you can buy from them to replace existing controls of X, Y, or Z. Why we are talking about open protocol? Because that is a big issue when it happens with the end user where he needs to access, but he's not allowed to do. In MCS, the Magnum one, you have different type of language to communicate with your BMS. You can have Modbus, lawn work, BACnet, MSTP, IP, any other like communication language. This is in brief what differentiates this open protocol to a proprietary protocol.
And maybe Chaleko, you can hop to the next slide. It's just there's a little video. We just took some screenshots. So this is an active turbo core magnetic bearing chiller that's installed, I think, in Minnesota. And these are just some screenshots from the video. So this is like, you can kind of tell on the right that that's what's popping up on the screen. And then you're in the upper right, you can see that they're, looking at things by touching a pen to it. So it's a nice little controller and decent graphics on it. Okay. Now, We're going to start digging into some of the questions that I had, and we're going to go, Ahmad and I will go back and forth. So starting off with which chiller to use, and maybe a lot of people already know this, but maybe not. Next slide, please. Yeah, so here's our basic compressor types. Now whether it's air-cooled or water-cooled doesn't matter so much. You can apply these technologies to both. So upper left-hand corner is that, if you remember from which chiller is a screw chiller, that's what it looks like in the upper right. It's the same compressor that goes on packaged heat pumps and packaged air conditioners. It's just probably bigger, but it compresses the gas with a very small motion. Dunham is well known for its screw chillers. There are two kinds of screw chillers. One is just a single screw, and this is a dual screw. That's what Dunham uses. I think there's some advantages to it. We may get to that, we may not. And then lower left is your centrifugal chiller. I think of it like a centrifugal fan. It kind of behaves like a centrifugal fan, or maybe a pressure blower. Then finally, in the lower right is a magnetic bearing centrifugal compressor. So those are the four types that we'll be dealing with. I think there are absorbers. I don't think Dunham makes absorbers, and we're not covering that material today anyways. So these are the four types of compressors that we'll be talking about, and really only three. For air-cooled specifically, thank you, ChatGPT. This is roughly what is available in air-cooled. Now, our scroll goes, or Dunham scroll goes all the way down to 10 tons and up to 180 tons. I think the market goes a little bit higher. I think there's a few people that make a 220 or 230 ton scroll chiller. Those are the packaged round barrel type compressors, and they're the least expensive. They have less staging opportunity. They're simple, and they cost the least. And as we go up in size and go up in complexity, we get into screw chillers and then mag bearing chillers. The screw chiller, our smallest size, actually isn't it 70 or 80 tons, Ahmad?
Yeah.
Right. So if you need more controllability, there's some option for you. And then finally, magnetic bearings. We actually go all the way down to 70 or 80 tons and up to over 1,000, and maybe 800. But we're going to cover those in a few slides anyway. So there's some costs and returns. So we're going to look a little bit closer at scroll chillers. Go ahead. Yeah, there we go. So, and when I look at this page, I see the capacity from 10 to 180 and then 10 to 100 with a V. I'm looking in the lower right-hand corner at ACDSV, which says single tandem or hybrid tandem variable speed. Can you just talk a little bit about the different ways you can have this chiller made, Ahmad?
Okay, now the V is just addition to you to know that we are using VFD or inverter compressors. If you don't have the V, that means it's the fixed speed compressors. Both are same. You have like the scroll, the capacity is changed only.
Okay. So with the one with the variable speed, is it the first compressor is variable speed and then the other ones are staged? So you're ramping up and down that one that's always working, and then the stages come on as your capacity goes up.
Correct.
Another question I had, and this is, I've talked to some other Dunham reps, so you have the options for different condenser coils. And I don't know for the life of me why I might want to change from a micro channel to a copper tube with aluminum fins to a copper tube with copper fins. Could you help me navigate that?
Sure. Now, based on your application, if you have severe environment around the coils, if you have acidity, if you have, like, let's say, sulfur plant, or I don't know which type of SO gases. So this will make your corrosion is very fast. So you have to pay attention to your coils. You have to pay attention for your coating as well. So
Okay.
microchannel is a single material. So it will not have a galvanic, it will not have metal to metal corrosion, but it will have the standard corrosion like galvanic or I'm not expert in corrosion types, but you'll have different type of corrosions. But definitely if you use single material like aluminum or copper, so you are eliminating one corrosion type, which is metal to metal.
I gotcha. What would be the advantage to going to an all copper condenser? Is the heat transfer better?
Again, yes, if you look item wise, yes, you'll get per heat transfer. But again, for you as a designer, as an end user, I should not pay attention just to the item. I should pay attention to the full system. If the item is so efficient, but the overall system, for example, is not that good efficient, what did I gain from that part only? Now, the trend happened in any industry. Everybody is looking to save cost, serve the customer, increase profitability, increase serviceability as well. Now, 30 years ago, 50 years ago, everybody was using copper aluminum or copper. Last, I believe, 15 years, plus minus, the microchannel came to the industry. I think pushed by Carrier, if I'm not wrong. It was good, everything is good, but now some of the cases like which came to me during my work tenure, okay, if the coil has leak, can we weld? No, it can't. You have to replace like a Lego game. You have to take that part, bring the new part and insert it. You can't just braze weld where you have leaks similar to copper or aluminum.
And there's also options that we're going to talk about a little bit later. You can have a standard fan, or you can have one of these higher end EC fans with lower sound on the condenser fans. Okay, so let's press on. And here's just a few pictures in the Dunham manufacturing facility down in Florida. So you can kind of see the V-shaped air-cooled condenser with fans on the top and kind of how the units put together before the sides are put up. But it's pretty, I would say, pretty straightforward. This led me into a question about talking about economizer for chillers. And I'm going to confess that I feel a little dumb about this one. So in case any of you are feeling dumb about it, I got a little frustrated because you can get, let's talk about what it does first, and then we'll talk about why I have all my frustrations later. So if you want to take your evaporator water and get some free cooling, you can put a little bypass. I guess, yeah, not really a bypass. You would run the chilled water through the free cooling section of the module. So if it's cold outside, if it's below your chilled water temperature, so it's in the 30s and below, you just run your evaporator water, which is your chilled water supply. I'm not sure if you probably run your return, right? Because that's warmer. Through the free cooling coil and back into the evaporator. And then you're not, either you can be running your compressor less or running it off. And so if you go on to the next slide, this is just kind of that bypass piping that goes around. So some considerations: number one, unless you're completely shutting down your air-cooled chiller and draining it, you're going to have glycol. And how much glycol is sort of a function of if you're using free cooling or if it's just freeze protection. And then that next point, are the economizer coils integral to the condenser, or are they a separate module? So some air-cooled chillers will have a water coil and a refrigerant coil in series, and then the fan on top. So if you specify free cooling, you may actually get a separate section that's bolted on. And you may have a free cooling section and then a condenser section. So it's important to pay attention to that. I think typically spools have an additional section and some of the other ones don't. If the economizer coils are integral, that may force you to go into a higher end fan. It may affect your sound. I don't know this, Ahmad, if your economizer is a separate module, does it require separate power or is it all powered up at the factory?
No, same power from factory.
Okay. And check your overall length. And then the part that I didn't understand, which this is one of those where you got to think about it for a second. We almost always use an air side economizer, at least for most commercial applications. And I suppose it would either be, I'm going to use a water side economizer to prevent a lot more outside air going into the building. And that would be a reason I'd use a water side economizer, or I'm just not using a water side economizer. And if anybody wants to comment on that, as we get near the end, that would be great, because this is, again, I'm learning too. Okay. So that's water side economizer. And now we're going to take a little bit closer look at the screw chillers that are out there. This was a really great video that I found. So Dunham Bush, you may or may not know, Dunham Bush had a pretty strong reputation in the United States in the 60s. And I just found this, this is so old school and nostalgic. But in here, they sort of show their initial screw chiller. Go ahead and play it, Chalikwa, and go to full screen. Make sure you're sharing your sound. I don't know if you did before.
Rotor. They are, for all practical purposes, the only moving.
Can you pause real quick, Chalikwa? I think we're just hearing your speaker.
Mechanism be more simple. And therefore, could any mechanism be more reliable? Dunham Bush took this unique technological concept and refined it, adapting it to our own finished product designs. Today, we are building the screw compressor into units of more shapes, sizes, and capabilities than any other manufacturer in the business.
I think that was cool.
Yeah, that was the gist of it. So this screw chiller is, I believe, Dunham Bush's maybe the original. I'm not sure, but we can go to the next slide anyways. So that's what it looks like up close and personal. And so we have two kinds of screw chillers. One's a horizontal screw, one's a vertical screw. And you can go on to the next slide, Chalikwa. And I'm going to ask Ahmad to talk a little bit about the difference between, they're both screw compressors, they both work. When might someone want to consider a vertical screw chiller versus, I think the typical is the horizontal, but can you expand on that a little bit for us?
Sure. Vertical screw, it was invented by Dunham Bush, I believe, 1967. It was like a breakthrough those days. They presented some ASHRAE show, maybe in Chicago. The main purpose was to invent this vertical screw, typically was for marine application, where you have unstable movements, but you need to have air conditioning. And at the same time, you should not lose your compressor due to unstable movements. So if you have like this, so oil level will be always up and down. That means you have a chance where bearings will be out of oil at a certain point of time. But in vertical screw, if you look at your right hand, you will find the lower part, which almost yellow. This is your oil. And the bearings are fully immersed inside the oil. Even if the compressors move, you are making sure oil will be always covering your bearings. So you overcome that issue for unstable movements. Inside this vertical, the suction from your left hand, then the discharge at the top part of the compressor. Before the top part, you have two types of two oil filters where you maintain almost 99.4% oil separation to happen within the compressor. This will give you more efficiency. This will give you also less noise as well. If you compare standard or horizontal screws compared to vertical screw, you will find somehow less noise from vertical compressor compared to horizontal compressor. Apart from this, both are in use. I'm not sure if all manufacturers, they have vertical. I think limited manufacturers, they develop their own vertical screw, but all manufacturers, they are using horizontal screws.
Okay. And then you and I have talked briefly, you can have a single screw design and you can have a dual screw design.
Correct. As a Dunham Bush, no, I don't have, but in the market, you will find some companies like Daikin, mainly Daikin. They use something called single screw. I don't know if you put some slide, but if you look to the conventional horizontal screws, it has two rotors. We call this male and female. In the single screw, you will have one main rotor. Then you have two small, like small circles, they call it gate rotors, one from this side and one from this side. So when it moves, those two gate rotors will do that compression side.
Okay.
You have bearing here, you have bearing here, you have bearing here. So you'll have like more bearings compared to horizontal screws.
Got it. Okay. Go ahead and advance. Select what? This is a cool video. So it's fun when concepts from one side of the industry pass to another. So if you've ever tried to turn down a centrifugal fan beyond 30%, you need to, and we don't do this often because we usually don't turn down fans that far, but if you block off part of the wheel with a mechanical device, you can get the turn down of a fan much lower than, say, 40 or 30%. And so there's a similar, of course, this is much slower moving, but we have a similar device to help us with low capacity control with a screw chiller, in this video sort of shows that.
The valve moves to a fully unloaded position. There's still direct compression happening, but it's just a very minimal amount. It may only be 10-20% of what that compressor's actual volume is capable of moving through it. As that slide moves and increases or decreases capacity, it's also increasing or decreasing our current load through the compressor. That is one of the main methods used to control how much we are going to stage up or down. Is what is our RLA? So we're going to run based off of percentage of our.
Yeah. So that's kind of a neat little feature about screw chillers, and that you can control capacity in part mechanically, and then also with your variable frequency drive that's on it.
That's why it's called like positive displacement when it moves.
Oh, okay. Okay, cool. All right. And so here's our air-cooled screw chiller lineup. So there's a difference between the horizontal and the vertical, but this is going up from 200 tons to 500 tons in the horizontal.
Now the new range, I know this is not updated, it's from us, but it starts from like 94 ton up to 500 ton plus.
Oh, okay. Okay. And then this is the vertical, which has, this one goes from 100 to 400, or does that change too?
Yeah.
Okay. Right. What's dumb question I should know? What's GWP?
This is a global potential, global warming potential. This is the ozone depletion. Everybody is tied with EPA, right? The standards of EPA. So they put certain standards you have to follow. Like last year, everybody changed from HFC to HFO, and GWP now became just everybody's saying, yeah, okay, this refrigerant, X amount of GWP, that refrigerant, that number of GWP.
Okay. Okay. So I'm aware of the necessity for oil management. And I didn't want to put a video in here. Ahmad and I talked about it, and he said, well, oil management isn't a lot of fun to talk about. So I just have one slide, and it's not very big. And I don't know if anybody will see my mouse or not, but we've got behind the black, which is the evaporator, or in front of the evaporator, we've got, yeah, go ahead, Chalekwa. We've got an oil tank, sump, and we need this to be able to run at any time for startup. So there's a little heater to make sure that the oil is viscous enough to get pumped. And then in the lower left-hand corner of that tank is a little oil pump. So we've got a controller that's going to measure the temperature, I think, and the pressure of the oil. And it's going to get pumped up to the compressor on the top towards the oil filter. And then there's a holding tank. So we need to make sure that the bearings of the compressor always have oil in them. And then as the oil falls through the compressor, it's going to get captured and then separated and then drop back into the sump. So it's got to be heated. Well, and there's also usually, correct me if I'm wrong, Ahmad, there's also a heat exchanger in case the oil gets hot. So it takes something from the evaporator to cool it off too.
Some designs, yes.
Yes. So yeah, so you heat it, cool it, pump it, spray it, separate it, collect it, and repeat the cycle. And at some point, your end user or you, the service contractor, is going to have to deal with the oil side of this machine regularly. And we're going to talk a little bit more about maintenance going forward, but that's the gist. So I don't know, specify for specifications, you're going to have some oil and all the little pieces and parts that go along with it, I think, is the gist of this thing. And I don't think anybody does oil management better than anybody else. I just think it's sort of a bolt-on. Anything that you want to add, Ahmad? I don't know if there's anything that needs to be added.
No, it's fair enough. But again, you have to consider oil same like your blood inside your body, right? If you need to check up, you have to do a blood test. So for chillers, you have to do an oil analysis.
Okay. Okay. Great. Now we're going to spend a little bit of time looking at magnetic bearing chillers too, not only just the chiller itself, but at the compressor. So let's go ahead with that. And maybe before we start in getting into the compressor itself, Ahmad, you can just talk a little bit about this unit. And it seems like you're, other than the water-cooled lineup, sort of your Cadillac.
Yeah, like this is, okay, Cadillac. I like Batman cars, so this is the latest product we launched as an ambush. It's air-cooled mag bearing, magnetic bearing, centrifugal chiller. We utilize the air-cooled concept as a condenser. We utilize mag bearing compressors, which has zero oil, oilless compressors. And this equipment is fully loaded equipment. That means it's not cheap. It's not just, yeah, I need 100-ton coolant for a commercial building. Yeah, okay, let me buy this. No, the budget is more expensive than that. So you have to have a real application to have such machine. Unless you are rich, you just need to drive Cadillac day, night, every time. So this is a standard, utilizes EC fans, not the standard fans. It utilizes, yeah, ECM fans, yep. And also utilizes always compressor enclosure. So that means this is very quiet machine. Always, if you compare to any chiller, this will be always super quiet. Also, you can add a free cooling coil, same what we explained previously, but next slide we will cover maybe more details about it. Also, you can ask for adiabatic cooling where you have dry weather, like Arizona, maybe Utah. And also you can have a quick start option in case you are utilizing data center applications where you can't lose the load for maybe 1 minute. You can't lose it. So you have to have like certain options equipped with your machine. Yeah.
Why don't you go on to the next slide, Shalekwa? Thank you.
These one of the like standard features. If you will go line by line, you will have some options. Some standard features are options in other like chiller categories. You have the choice to use like microchannel coil or copper aluminum coil. You have the choice to you don't have choice mainly, but it's a standard, like it's a compressor enclosure, it's EC fan. So your choices are limited in these features, but in next slide, you will have more options to add. This is the free cooling diagram. In ACM, we utilize an integrated coil. It's not just additional coil to the chiller, same what we presented, Tom presented in the scroll type, where you have extra V coil with fan and the expansion tag. In ACM, we utilize same DX coil. If you consider this is your coil, DX coil, the condenser, we add here another coil for the free cooling. So you save the space. You can utilize at very low ambient temperature, 100% free cooling. That means zero mechanical load from your compressors. So you are switching off your compressors. You are not paying for your power, but you are utilizing your 100% free cooling from that integrated coil with your EC fans. We use logic of EC fan will be like the shared EC fan based on your ambient temperature. We need delta T around 5 between your supply temperature and the ambient, so the free cooling can work. It will be 10-15% load, and it can reach 100% load. Now, it goes by EC fan based on the pressure. One of the question was about what will happen about the like dirty condenser coils. Now, based on your pressure, EC fans will work like high speed, lower speed, because it's ECM. It's like from 0 to 10, so infinite steps of speed. Now, once it reached to the lower pressure set point, it gives command to the compressors to switch on or off based on your like ambient and your design. And if you look, you will find like butterfly valves, solenoid valves, to make sure the cycle will happen based on your like partial free cooling, partial mechanical load, or 100% free cooling and zero mechanical load.
With the free cooling, Ahmad, are all those valves, are they field installed? Are they part of the chiller integrally that comes out?
No, that's within our condenser coil, within our chiller frame.
So I'm talking about your 3 isolation valves to direct the chilled water back through
like
the condenser
two-way
section.
modulate. Yes, you have two-way modulating valves.
Uh-huh.
You have isolation butterfly valve.
But they're installed. They're not
Yep.
loose.
Yep.
Okay.
Yep.
Okay. Got it. Okay. And then, sorry, this slide's a little bit smaller, but yeah, so this is an oil-free compressor. I think it's a Danfoss, no?
Yeah, turbocore Danfoss.
Okay. And I think our next slide, we're going to play a little video. I thought this was kind of a neat slide. There's a couple things in here that remind me. Can you pause just, before we start, go to full screen, please? One is just, we've got a centrifugal, basically a centrifugal gas mover, not so different from a fan. So part of this is talking about the inlet vanes that go on the compressor. And then the other part of it, it's going to show this permanent magnet structure, which is not much different than these EC motors that we're putting together, which has permanent magnets in it as well, and whether it's an EC as a single phase or a three-phase permanent magnet, same kind of concepts, just increasing efficiency. So let's play this and get everybody up to speed. It's interesting.
For the mechanical parts, we see the inlet guide vanes at the front on the suction inlet. These blades can vary their position and cause a refrigerant to swirl as it enters the compressor impeller. These are driven by an internal stepper motor. The serial driver module controls this motor, and the bearing motor compressor controller determines when and how much to rotate them. These are used during low cooling loads to improve the efficiency and avoid chiller surge, but in normal operation, they are usually left open. Then we have the two-stage impellers. These rotate together. The refrigerant passes through the first impeller and then through a small channel and into the second impeller before entering the volute. From here, it will be ejected from the compressor. The refrigerant pressure increases each time it passes through an impeller. The impellers are attached to the shaft, which runs the length of the compressor. The shaft passes through the electrical motor stator. The shaft contains permanent magnets in the rotor section. These will interact with the electromagnetic field produced by the stator coils of the motor. And because magnets attract and repel each other, we use this to force the rotor to rotate. The variable frequency drive controls the speed of rotation. The bearing motor compressor controller determines the required speed.
Great. Okay. And I didn't add a lot of slides for water-cooled systems because basically we're trading the air-cooled condensing unit section for just a water condenser, and we already know about the shell and tube vessels that we have. So Dunham manufactures water-cooled chillers using scrolls, using screws, and using turbo core compressors. So, for example, this one goes up to 880 tons. I'm not sure how big the screw machines go, but I think they're that size or more. So this offering is for both air-cooled and water-cooled in all the different compressor types that I've shown you. I just didn't know how long we were going to go, so I didn't want to muddy up the length of this thing. But this guy goes all the way down to 75 tons and up to almost 900. It's probably bigger now. Yes, Ahmad?
Yeah, 1,000 ton, and we are developing with downforce compressors, bigger compressors. We will be 1,400 ton maybe by end of this year.
Great. Okay. Then this is just something I added, Ahmad. Thinking about the tightness, like how important is the discharge or controlling your water temperature? And if you go to the next slide, please. I do this sometimes for other systems in that, how tight do we really need to be? And if your design for an air handler VAV system and you've got a lot of return air and you've got a mixing ventilation system and you're open loop on humidity, your temperature control, you could probably save energy by keeping very tight chilled water temperature controls, but it's not absolutely necessary. Whereas, if you're going to do a chilled beam system, if your DOAS system is going to be tightly controlled, if your heat pump or VRF systems don't handle latent load, then it may be time to switch, like moving from a scroll chiller to a screw chiller. It just goes to how tight do I need to be? And I think a lot of times people just pick chillers based on what the budget is, but it may not be, it may be just something to consider that we use tighter controls depending on the system and looser controls depending on the system. And I'm sure designers take that into account, but sometimes like I need a chiller And we got to think about those little details about the controllability of it. So that's all I had on that particular subject. And one more slide here before. Oh, folks, we have a guest speaker that's joining us, Jackson Popple from Price. I'm going to turn it over to him in just a couple minutes. So full load, part load conditions. So if you're looking for a chiller, you're going to go to AHRI and next slide, please. AHRI, and you can find these Dunham Bush chillers listed. The AHRI catalog is really fun in that if you change, like let's say you change your condenser fan from one to another, you're going to get a different model. So those are samples of Dunham Bush listings, the AHRI directory. And if you go to the next slide, in the background is a picture of a big test facility that Dunham Bush has. And in it, I mean, I've done talks about test setups. The chiller one seems to be very straightforward. It's okay to produce a certain amount of tonnage, how many kilowatts does it take? And then to do the integrated part load value, you have set parameters of, I think, 75, 50, and 25%. And so you get a different grade. And you use those for your, if you're doing an energy analysis, those are going to be important. But I didn't find a whole lot of, I'm sure like down the line as we do more and more chillers, I'm going to find something fascinating about test setup stuff for chillers. But for the time being, I think you just need to know that they're tested. In Florida, we can do a run test. We don't have the ability to do a climate controlled air cooled run test. So if you want like specifically an air cooled test at 95 degrees, we're going to lean on the ambient temperature to get you close. That's the only real caveat I'd say about test procedures, but I would just use the test data that's listed in AHRI. It's a pretty stringent test. Anything to add there, Ahmad?
Yep, we can do as per prevailing ambient, as Tom said. We don't have a controlled climate chamber. We have 3 certified HRI test stands, 300, 500, and 1500 ton. For work cooled, we can do as per your design. We utilize the cooling tower.
Great. Okay. And I'm going to come back to maintenance. Chalekwa, can you go a few slides up and let's get Jackson on here. Okay, this is one that I thought that I was going to be able to solve myself. So first of all, let me introduce Jackson Popple from Price Industries. He's part of the noise control group that does so much for airflow. So thanks, Jackson. And I wanted to, I know we get calls like, hey, we got a property line problem with an air-cooled chiller. And Jackson, I'm sure you get more than enough of these, right? And they're always really fun to solve after you put the chiller in. Really fun. So I thought I'm going to do this myself, and I'm not going to need to use Price Noise Control to help me out. And then I got 2/3 of the way through, and then I called Jackson in the panic to help me out. So I'm going to show you the step-by-step approach I took to get to where I couldn't go any further. So if you select a chiller, you're going to get some sound data. Hey, first of all, great. It's in all 8 octave bands. And so this is for a scroll chiller, all the different sizes. Note, we're for property line issues, we're really dealing with, the 250, 500, 1,000 bands. And notice like between 180 ton chiller and let's say 40 ton chiller, there's a 4, 5, 6 dB spread between all those. So dropping the size of the chiller certainly doesn't drop the sound that much. I mean, 5 dB is consequential, but know like, hey, I'm working with the biggest chiller here, but the smaller chillers aren't necessarily going to be non-problematic. So I'm like, okay, I've got a good start here. Next slide. oh, look, I've got some options for, hey, if I'm going to buy an air-cooled chiller, I'd like it to be quiet. I can just plug in right here and get a compressor jacket or a low fan noise option, or even on the next slide, I can get both. But then I go, wait a minute, this is not sound power levels, this is sound pressure levels. Oh, now what do I have to do? So, all right, I can do a little bit of work here. Not very difficult. Next slide, I grab 4 different similar sized chillers. These are all Dunham models, and I've got the sound pressure at different distances. Okay, so far, so good. But I need to convert these to sound power levels so I can use crisis analysis tools to see if I'm going to have a property line problem, or if I need to put a wall up, if I need to buy a sound package, et cetera, et cetera. So now I've converted those sound pressures to sound power levels. So let's take our 180 ton screw. I'm at 66, 76, 83, 92, 94. When I see 90s, I'm thinking about at least fans and rooftop units. I go, those are starting to get a little bit loud. So this is an easy conversion to make. You just need to know the distance and the conversion. So I've taken these 4 chillers and I dump them into the next slide, which is Price's acoustical predictive software. So not only does the acoustic predictive have duct path analysis, it also has radiated sound analysis. So upper left, the 180 ton scroll chiller, that's the raw sound power levels. And what I did was I plugged in, you can see at the bottom of the screen, I put the receiver at 150 feet. So I'm at a school, I'm at a building, and at 150 feet away, I've got a property line restriction. Maybe your property line restriction is 55 dBA during the day. Maybe it's 45 at night. Maybe it's 50. But as you're looking through these, and I threw in a Daikin one too, we are not free and clear at 150 feet away. We're probably going to be needing at least to look at sound treatment for the chiller itself or a barrier wall. And these are not the biggest chillers in the world. We make chillers up to 500 tons air cooled, even bigger. So this is a good starting point. And now I'm going to have Jackson take over control here and bring us the rest of the way with how we do a sound barrier analysis. Because I wanted to know if I put up a wall, if it was going to do any good or not.
Yeah. Thanks, Tom. So I'm going to steal a screen here. Okay, perfect. So basically I kind of took that same sound data that Tom had, and I also looked at it. The one thing I did notice when I was looking at it was if you look at these values, and this is just the cut sheets for the sound pressure data that we have, we can see it's a lot lower in these 63, 125 hertz bands than these middle octave bands. And that's kind of, it's usually not outright stated for the most part, but it's kind of a giveaway that these are actually A-weighted numbers. So it's in dBA rather than dB. So what it is it's a sound, like we do need to convert it for distance from sound to sound power, which is shown here, but this is still in dBA, where we need to get it down into dB down here and change that over, which is another kind of easy conversion. It just basically what dBA is that it weights your octave bands similar to NC would, if you know anything about that. But basically the lower octave bands, since they are like lower bass frequencies, the human ear doesn't have as much difficulty with those, so it weights them towards or weights those higher. So you can have a higher sound level in those octave bands for A weighting and still kind of hear the same or perceive the same loudness of noise. So that's what dBA is trying to do. But what dBA is just these deductions here. So the minuses would be, we're gonna have to add those back in. There's a few over here that are actually gonna add sound to it. But anyways, so what I did was take our noise that we've correct.
So to recap, I did it wrong. Perfect.
Yeah, I mean, it's tricky because a lot of the you kind of have to just see a lot of them to know. And it's not really stated anywhere for the most part. So, and it is tricky. It doesn't change a lot of things a lot of the time. If we go into where I plotted these in, you can see it's only like a couple dB here or there. But on some, if your lower octave bands are going to be driving the noise, then it's going to, change that quite a bit more. So it really depends. It's not usually stated, so I just wanted to mention that while we're in here. But so once we have that all changed over, we have like raw sound power in dB. We have that in here. We can look into our receiver. We can see a lot of these are right around where we want to be. They're all a little bit higher, except for the scroll chiller with the sound package than the 55 dBA that we're looking at. But I mean, even with this, if we look at the receiver, this receiver is pretty ideal conditions. It's going to be 150 feet away, which is, probably what we're going to see, but it might be further than what we see. And then it's also got this directivity factor of 2. What that is if I pull up this, basically these should be kind of flipped. These are shown as they would be for duct systems. So think of this is the ceiling, but in our case, we're going to be looking at it for the floor. Basically, what the directivity factor of 2 means is that your chiller, your rooftop equipment, whatever it is sitting on an open roof with nothing around it, which hardly ever the case. You're likely always going to have more than one reflecting surface. So in that case, I'd probably go with a directivity factor of 4 or even 8, just meaning that maybe you have a wall right behind your chiller, or maybe you have a chiller beside it, a low wall behind it, and then the roof as well. All are going to be reflecting surfaces, and those are all going to contribute to the noise. Reason we might want to do that is that if we go in there and we look at it, now we're at 54 dB. If we change it to 4, and if we change it to 3, or 3 reflecting surfaces, we're at 57 dBA. So that's a 5 dBA change, just depending on where this is installed, what kind of is around that chiller. Just kind of more into, I guess, like the whole noise package is good. And, even from the 180 ton, if we do the same thing with no noise package, we can see, we are getting a, appreciable difference there. 7 dBA is not, it's like, it is going to be appreciable, but it still might not get us down to where we need to be.
It's a call and a problem where you end up on the job site with the architect, the owner, and everybody's pissed off because they're responding to an angry neighbor. And God, this must happen all the time. And I suppose, I'm a pickleball player and I hear all about like the neighbors being pissed off about pickleball. I can only imagine the constant air-cooled chiller noise is not going to be well received.
Yeah, and especially, air-cooled chillers, fans, everything, it'll come up. So, but there's solutions for it. So what we do have is a barrier wall element. So I've disabled it for now, but I'll go in and enable it. And this is all in our software. If you do want to download the engineering edition, you can play around with it yourself. It's just on our website. Tom can help you out with that as well. But once you get into here, you have these different variables, and we're trying to figure out, kind of what we're actually looking at. I did do a little bit of a diagram. I'll also pull up this this ASHRAE applications handbook. So this is what we're looking at. Basically, we're trying to find the path length difference, which is dependent on how high the source is off the ground, how high the receiver is, how high the barrier wall is, and then how far from each you are. And then based on that path length difference, which is just A plus B minus D, which A is this distance, B is this distance, D is this distance, you're going to get a set insertion losses or transmission losses from your barrier. What this is just the noise going over or around the barrier. This isn't the noise going through the barrier, but we can also, and I'll show you after, do a different, just do a slightly different path to show that noise through the barrier. Likely the noise going around or over the barrier is what we're more worried about anyway. So with that, I'm going to jump into my lovely paint sketches that I've made just to kind of demonstrate what these different variables are. But let's say we have a chiller, which is our source on the roof. We're looking at putting a barrier, and we have a receiver down here. We don't know exactly how high we want our barrier to be, but we kind of know where it's going to be, where the receiver or property line in this case maybe is, and how tall the building is. So if we do that, so our first two variables, if we go back to here, are going to be distance from the source and distance to receiver. So distance from the source, if we go back here, is going to be, I marked it as DS, and distance to the receiver is DR. So these ones are fairly simple. It's just how far are you from your source to your barrier? How far is your barrier to your receiver? Let's say in this case, we put up the barrier wall. We need a little bit of clearance between the chiller and the barrier wall. So we put it 5 feet away, and then, we're 150 feet away in total. So we're 145 feet from the barrier. So that's all well and good. We have this. I'm gonna just zero these out for now. So then we have our 3 different heights we're looking at. This can be a little bit confusing because let's say, we have a 10-foot chiller and then we want to make a 12-foot barrier wall, and our receiver is a person at the property line that's 6 feet tall. If you go in and put in all of those numbers, you have a 10-foot and then 6 foot. It's going to still work, and there isn't going to be a lot of issues, but it's not really right because we don't have the same zeros for all of these. Our barrier and our source are both going to be on top of a building where we're measuring the 0 from our receiver at the ground. So the 0 for all of these should be the ground, which I kind of did here. And then if we say our building's, I don't know, 20 feet tall, and we go back to our our analysis here, that would mean since our chiller's still 10 feet tall, but our building's 20 feet, then it's going to be 30 feet. And we might need to change the receiver height, sorry, is still going to be 6 feet. And then the barrier height will be 32 feet. Just knowing exactly what we're putting in there. In this case, it doesn't really change much because the path lengths are pretty similar in that case. But once you get into bigger distances, and I'll maybe go into my sketch again just to show, because I did kind of mark up what these are going to look like. So, our A, B, and D are going to look like this in this case. But if we had used the other, heights, our A, B, and D would look more like this. And once you get into bigger heights, longer distances from the barriers or shorter distances as well, it can mess with it and end up giving you kind of the wrong losses you're looking for. But anyways, so just making sure we have the zeros at the right point. In this case, it's going to be, we want to put the 0 where ground is. So once we do that, we go back in here and we look and we see, okay, so we put a barrier wall on this 180-ton scroll chiller. How does that compare to that noise package? Well, we can see it now, with the receiver being the same, everything else being equal, this barrier wall is doing, if we just kind of click enable, disable, this barrier wall is going to take it down 14 dB, where that noise package took it down 7 dB. So, that's going to, around 10 dB is about having the sound. So we're going to be from just under having the sound, so maybe 3/4 of the sound, to, just over having the sound. If
And
that
that was,
so like,
that's because of all the directionality, that's the sound around the barrier.
this is the sound, this would be the sound going over top of the barrier, kind of in this case. What we're assuming is that like our barrier, like, so if we look at it top down view, I guess, what we're assuming is that our barrier is long enough so that sound isn't going to go around, or
Okay.
we've made like a U-shaped
Pushing
barrier, kind of, because it does have to be longer. You can't just put the barrier, just in front of here, because then the sound can just obviously go around. But yeah, this would be, or what we'd be trying to simulate here is more the sound going over top of the chiller.
Got it.
Yeah. What we can also throw into here just to check, and again, most of the time the noise going over top of the barrier is going to be the issue, but we could build in a branch here and have the same receiver. So I'm just going to copy that over. And then throw in a acoustic panel. And this one's a 2-inch panel. And just say that.
That's the straight through. It's like.
This
so
would
much
be
more.
what's through the actual panel itself, because this is the transmission loss of the panel. So in this case, we're going to be more worried about this sound going over top of or around the barrier.
Got it.
Yeah. Yeah.
Cool.
Yeah.
So yeah, I did take a little bit of a left turn in this presentation, because when I started putting my questions together about chillers, I wanted to know when I was going to run into a problem. And then when I found out that I was doing it wrong, I figured everybody was probably in a similar boat where they're not acousticians, and they go, I'll throw some money at an acoustical package and assume it's going to work. And maybe that's not the right recipe for all of us. So it's, Price will help out with chiller analysis for free. And when I learn how to do it, maybe I'll be free too. But if you have an air-cooled chiller, it would be worth your time to consider whether or not you have a property line constraint or no. So awesome. Any Q&A for Jackson before he hops off? And I'm asking you, Chalequa, and our audience.
Yeah. And I guess while waiting for that too, as Tom said earlier, the earlier we can be involved and like look at this is always better. It's always harder to do after the fact. It's more costly. There's more analysis to do.
Well, we just need steel.
Exactly.
A barrier wall without steel. So getting the steel in is very inexpensive on the front end of the job and really expensive after the roof's in.
Exactly. Yeah.
Okay. Well, if there isn't anything, Jackson, thank you so much for hopping in and joining us. Did you say something, Chalequa?
Oh, just saying there's no questions
Okay,
so far.
that's good.
Yeah.
So let's turn it back to the airflow events screen. Jackson, I will see you around. Thanks for hopping in.
Yeah, no problem. Have a good rest of your day, everybody.
All right, appreciate it.
Hey, see y'all.
And then Chalequa, if you can go back a couple slides, we're just going to talk about maintenance real quick. Okay, great. Forward and yeah. So from our quiz, we learned that it's important to clean our condenser coils. And then if you also have an economizer coil, you need to clean that too. And so why do we do that? Well, if we're not condensing our refrigerant to a liquid, then we are using additional compressor energy that we don't need to. So this is for your customers. You have to power wash the condenser coils, and then if you have economizer coils as well. And then, of course, the oil maintenance needs to be taken care of. The refrigerant charge needs to be inspected. I'm on the part where it says nothing for the actual compressors as far as maintenance goes. Is there, I mean, I know a scroll compressor like the ones shown here, you can't really crack them open. So there isn't maintenance there.
Yeah, there's nothing called maintenance for compressor unless you have a full breakdown. But based on your oil analysis, you will come to know what you need to do. Like sometimes you require full overhauling.
Okay. And then scrolls are usually replaced, I imagine. And then screws and centrifugals are
You can service it at site.
Okay. And then the evaporator, there's not much to do in the evaporator for an air-cooled chiller, typically, not in your routine maintenance. At some point, you may need to punch those, but I don't think that there's a lot regularly.
Yes.
And then, Chaluk, was there, I don't think there's a video with this, but this is just showing, this wasn't a bad little video. I didn't plug it in, but it's basically, so you see all the bolt holes, you know, you drain that chiller, right? This is for water cooled. And then there's just this little punch thing where you squeegee out the tubes, whether that's water in the tubes or whether it's refrigerant in the tubes. You're just cleaning them to make sure that the path for the refrigerant or the water is clean. So I remember going to a job site when I worked at Johnson Controls and seeing someone having taken apart this chiller, and I'm like, oh my God, they must be a rocket scientist to do this stuff, but it's really sort of a pretty simple thing to clean those tubes. And then as well, you know, we've got the same oil service. You may need to service both the condenser and the evaporator in a water cooled. But again, it's very mechanical, not particularly difficult. And when I think about like, oh, there's a problem with the chiller, at least people know how to deal with it. Like if you have a problem with the VRF system, there's a lot of sort of head scratching about what needs to be done and which software revision do you have, and et cetera, et cetera. This is pretty, as far as I'm concerned, pretty efficient and pretty straightforward. Okay, and then we can go continue to, we've gotten the last of this. Okay, we have two analyses, and this is our second to last segment, but energy savings and water cooled versus air cooled. I attempted to do this again on my own using the power of AI. If you can go to the next slide, please. I used Train. Why? Because I think Train's just said, hey, use a Train chiller. And compared a CentraVac versus an RTAC, which is rooftop air cooled, and just roughly these kWs per ton. And so I said, okay, let's use Milwaukee and let's use 150 ton constant load. Will you ever have 150 ton constant load year round in Wisconsin? You will not, because you could use an economizer and your load isn't going to be continuous. But if we're running these things all year round, how did they shape up? So let's go through the next slide and just review the couple of parameters that we had. So here's our bin hours. This is Mitchell Field bin hours. So very few hours, of course, at the hottest temperatures. So, and this is GPT's verbiage. So our kW per ton drops significantly in those bins when they're colder. And two more slides, please. We got an 8% efficiency penalty for air cooled in Milwaukee. Now, is that deadly accurate? I don't know, according to this, it was like $90,000 to run a 150-ton chiller over the course of a year continuously. I don't know if that's deadly accurate, but I just see, based on the same set of parameters, that air-cooled isn't a very big penalty here. And if you have a constant load, you use a water side economizer, maybe that's not so bad. This is not a great representation, but I used the tools that were available to me because I'm not doing an analysis. What I find fun about this is I asked a handful of people, hey, when do you switch to water cooled? They said, I don't know. I asked someone in the office because you're generally, as a consulting engineer or a contractor, not paid to do a full analysis of air cooled versus water cooled. So all I'm sharing here is maybe the penalty for air cooled isn't so bad. And certainly the complexity goes way down without that cooling tower. And then I'm going to turn this over to Ahmad. This is a far more elaborate study on air cooled versus water cooled. And we're using a water cooled centrifugal versus an air cooled screw. And do you want to hop in here, Ahmad?
Yep. This was done based on like a real example. We did 2,560-ton air-cooled system and water-cooled system. This was done in Dubai, UAE. So first, you need to understand the lifetime of your equipment. So the standard, which we manufacturers claim like 15 years for air-cooled, 23 years for water-cooled. Sometimes they will say 25. We use same refrigerant 513A, so there is no like differences in efficiency, because sometimes if you change from refrigerant to refrigerant, you change the efficiency itself. So we use same refrigerant. In water cooled, we use the 3 chillers because you can get bigger, larger capacity. And in air cooled, we use 6. So you need to keep an eye at your space when you design. Do you have space for 6 chillers, 6 pumps, 6 pipes? Air cooled will be like maybe 8 meters, 10 meters, compared to maybe 5, 6 meters as water cooled. So you need to keep an eye on installation part as well. Then the part load, when you go down, 15%, 10% for air cooled and 10% for water cooled. So it's almost near to each other. Now the connected load, this is based at T3 conditions at HRI. So you will have 1,900 O2 ton from water cooled and 3,744 ton from air cooled. Based on the rates in Dubai, so the cost for the first system, the water cooled, 3.3 million dirhams, the local currency. I think 3.7 dirhams equals to $1 in that range. So you'll get more like $1 million, maybe first system. The second system air cooled, 5.8 million dirhams, like 1 point something million dollar. This is your chillers only, because for sure you will have AHUs here and here, fan coil units, VAVs, everything will be almost same inside the building. Now, for air cooled, you have different accessories, items to add. For water cooled, you have another different items to add to complete your system. So the approximate cost for the cooling tower condenser pumps, this is only for water cooled, and another like amount, which you see, 450,000 dirhams. Sorry, 1.4 million dirhams, and 0 for air cooled. Then the installation itself, the labor, the pipes, everything else will cost you for water cooled 450,000, again 720,000 for air cooled. Now, if you will sum up all the accessories, you will get 1.1 million dirhams, 0 for the condenser pumps and cooling towers. If you will add the water treatment, because you need water treatment to your chilled water, like a water system, because you have cooling towers, you have water and condenser, you have evaporator. Another cost Then do your capex. You will get 6.6 million dirhams for air cooled and 8 million dirham, almost approximately, for water cooled. If you go to next,
It's more expensive than I imagined.
if you go to next, now you have your also annual operating cost. Now you have to consider part load, because as per ASHRAE, you are running 1% at your full load, 99% at your part load. So if you do some analysis, you'll do that calculation based on the like kilowatt rate on your area, then you will get 1.9 million dirhams for water cooled, but almost double that, 3.2 in air cooled, because it's less efficient than a water cooled system. Then your makeup water, you have additional 500,000 for water cooled. Then the water treatment per year, additional 63,000. Then the annual operating electrical cost, cooling towers, condenser pumps, because this is only for water cooled, then another 267,000. Then the maintenance cost per year for water treatment, another amount. Then the main cost per year for chillers, cooling towers, and condenser pumps, 360,000 for water cooled, 150, almost half for the air cooled. If you do this OPEX summation, you will get 3.2 to chilled water, like water cooled chillers, and 3.3 almost equal to each other for air cooled. Now, if you go next, now you have your total capex and OPEX for first year, then the 5 years, you are getting old and old and old. If you do this analysis, you will come after 15 years or even 10 years, you have almost break-even point for air-cooled and water-cooled. But after that, you are saving on your chilled water. So as a designer, as an engineer, you have to look for your application, your OPEX, CAPEX, everything to determine, should I go for air-cooled? Should I go for water-cooled? In certain applications, you have no choice except water-cooled, regardless whatever you'll try to do. Assume you have a limited space, you have 5,000 ton cooling load, but you can't just put maybe 20 air-cooled chillers. So you have no choice. So this what determines your design criteria.
Right. So even at half the operating cost, all the other, basically you're at a dead heat till you replace the air-cooled chillers with new ones. You get 2 runs out of the water-cooled versus 1 out of the air-cooled. Although, I don't know, do you replace a cooling tower, or do those, maybe, I don't know, we don't need to do a cooling tower class, but it's surprising when you look at all of it. I could get cases for both, right?
Yep.
Yep, fair enough. Thank you for that analysis. And of course it would be different here. I'm trying to think, so if you colder climate, the runtime is going to be fewer, but I don't know that the air-cooled chiller lasts any longer because it resides in Wisconsin. I would imagine it would be shorter, the same.
Mm-hmm.
So interesting. Okay. I just threw in these last handful of slides that, which I said I wouldn't, but I did. So, so Dunham manufactures the water-cooled version of their screw chillers, and both the vertical and the horizontal. And then on the right, we also have the ability to add another shell and tube heat exchanger and make it a heat recovery device. And if you go on to the next page, Dunham out of Malaysia does ice storage, and we also do some air handling. So we do modular air handlings up to 56,000 CFM. We haven't been bidding a lot of that yet, but we are going to be looking at it. So, and then finally, last slide here, should I add Dunham to my chiller lineup? And I've given you a few reasons why. And I'm not, well, I'd love to read it to you actually. You're here, so you probably at least kind of like us, probably more than like us. Now you've seen what Dunham Bush has to offer, and maybe it's a good fit. One thing that I put in my posts is that lead times may become more problematic. There's 2 huge data centers that are coming up in Wisconsin alone, plus data centers all over the world. We do give a shit about making sure we do it right, and which is part of the reason why we're having this class. We don't bundle our equipment. This air-cooled magnetic bearing chiller is a really neat offering. Dunham Bush may be a little bit quieter than some of the competitors. Our pricing is competitive. And last point for you contractors, Dunham Bush and Airflow are not going to be calling on your end user to sell them a service contract. We're going to be servicing our customers, not your customers. And so just something to keep in mind. So with that, I can't believe that it timed out like this, but it did. I thought on one hand, we're going to be done in 40 minutes. And on the other hand, I thought we had 3 hours of content. But here we are bringing in to the end. I'll open it up for questions. You can stop sharing the screen or sharing the deck, Chalekwa. And I see a couple of Q&As in there. And Darren, I'm glad you now can scroll. If there are Q&A questions, then let us know. Other than that, I would like to say thank all of you for attending. I'd like to thank Ahmad, who did a really nice job supporting me. I don't know, I must have emailed Ahmad 100 times to put this presentation together, and he always responded so quickly. And then I also wanted to thank Jackson for doing a great job on the acoustics. And finally, to Chalekwa, who's trying to run this in the background with me trying to direct traffic. So if that's that, you'll receive your PDH credits, probably not this week, but maybe late next week. And of course, you can always email me, the engineering group, Caleb, or your salesperson, and we'd love an opportunity to help you with a chiller. So thank you all very much, and we're going to sign off now.